So I do that. Hi everybody, and ho 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 from Melbourne. So welcome to this last session of Vsaonline in 2022. So happy to see you all here, and I hope some more people will join along the way. So today is a special session, as you have seen in the announcement. So we're thinking to try this open discussion or panel-like discussion, discussing the current work in progress as well as future directions in VSA HDC. And so not to overcomplicate the moderation, so I outlined some procedures in my email. So the idea is that we go around the table, so we have several questions to answer, or I will ask several questions to you. The first question is, where are you from? So to briefly introduce yourself. So the current work that you are doing, or if you're wishing to share this information. And the last question, so what you consider as the challenging task to spend time researching on, focusing on within HDC VSA. So that's more or less an agenda. So, and I don't know, so I see many more people have connected. I'm so glad to see you. If possible, if you have cameras, please switch them on. So we at least we'll see faces of each other. But let's start. Maybe I don't know, is there any volunteer to start? I don't want to draw a blanket over myself.
We're all shy.
Yeah. But I was expecting this a little bit. Therefore, I probably will start with a random pick. So Kenny, my eye is kind of looking on you. So maybe you can start.
Yeah, sure, no problem. Yeah, first starting introducing myself. I'm Kenny. I'm from the Chemnitz University of Technology at Germany. And yeah, I'm a PhD student and working in the field of mobile robots and yeah, some other autonomous systems like autonomous cars and so on. And yeah, my topic is related to computer vision and signal processing, especially, for example, time series classification, as you have seen in the last talk here in the VSA webinar. So yeah, it's related to this topic, and there we are using VSA to encode more explicit information into the system, and yeah, hopefully it makes it better. And from my side, one bigger topic, or for me it's like a topic which is, or an idea which is somehow fuzzy and not really concrete, but as I have visited this year a summer school in at Caltech about the neurosymbolic programming, one idea I have for future work is to use this maybe mechanism and incorporate it for in VSA. So I'm not sure if somebody is familiar with this topic, neurosymbolic programming, but it is the combination of the two topics of symbolic approaches, like will-based approaches, and on the other side, neural approaches like neural network. And the idea is to compose these two topics and learn faster and are able to interpret the resulting model. And an idea is to use it maybe for VSA, since VSA are also using some operations like ANDs and ORs, also rule-based, like the binding and bundling, and maybe construct some structures which are learned. So the most time these operations and equations are handcrafted, and maybe it can be also learned, but it's somehow fuzzy and not really concrete. It's a guess and a thought about this topic. That's a somehow long-term topic, or I'm not really sure if it makes sense or not, but it's one thought from my side about the one possible topic for the future.
I think we can also infer a rule that you can, I mean, everybody can, anyone can just jump in. So so keep your microphone unmuted. So jump in with some comments and questions, or I mean, questions, maybe comments, rather comments.
I have a like semi-opinion, semi-question here. So I'm not super deep into neurosymbolic AI, but to me it always like whenever people start talking about neurosymbolic AI, it feels like it should be, you know, for VSA, it should be almost home, right? Because that's what we usually begin with, right? The symbols, random representations can be assigned to create symbols, and from that on, like you have separations and you can manipulate them. But at the same time, it's like whenever you start like reading deeper into the articles, it's like you're in a totally different universe, you feel like, because it's often a lot about like maybe some special constraint that you can make on your neural network. So to, you know, to make some sort of bias to the network so that it would better adapt to your problem and things like that. So do you more see the advantage that the neural symbolic models could come like as a way to maybe interface the raw data and obtain distributed representations, or what is your opinion on that direction? Like what, in what way should sort of the, you know, the combination go?
My guess or my hope is that maybe the neurosymbolic approach can be used to create the equations, so whether using binding or bundling, so composing these vector symbols, so these hypervectors, in a similar way that it has been done in these neurosymbolic approaches with these rule-based operations like ANDs and ORs. So it's related in that way, I think. And actually it's like constructing a graph with all possible operations like binding and bundling, and neurosymbolic approach can be, for example, used to find the best combinations of all possible combinations and operations between them.
Thanks.
Could I just jump in there? Just that's just reminded me that people might not know that the NESI neurosymbolic people have just recently started a Slack group. It's open, anybody can join it. They're currently up to about 500 members, they say. So if anybody wants an invitation, probably the easiest way to have a look at what they're doing is to join it. Anybody who's on it can issue invitations. I'm on it, so just message me directly and I'll send you an invitation if that's what you want. But yeah, I'll back up what Dennis has said historically, and that they seem to have been either hybrid classic AI plus neural networks, or trying to persuade classic neural networks to do symbolic things. Now that might be a gross mischaracterization on my part because I haven't followed them closely enough, but I haven't seen any evidence so far that they're trying to pick up neural systems which already have the algebraic structures you'd want to make it easy. But anyway, yeah. So if anybody wants an invitation to the Nessie Slack, just send me a message and I'll send you an invitation.
That's the workshop, right?
What is absolutely true and important is what Dennis also said, is that VSA, I mean, one of the promises is really on the symbolic side. And this wasn't yet developed to a greater extent. So that would be something to look at. Moreover, I mean, from my side, again, so this is really not concrete thoughts, but in many of the modern successful deep architectures, so that they well, like auto variational autoencoders with quantization, even the attention of based architectures. So people learn some, I mean, learning representation is part of the architecture. But so it would be kind of interesting to see whether you can include more structured or VSA encoded structures in this learning pipeline. But again, so I don't have any more concrete formulation on this side.
Yeah, I think it needs more investigations on possible applications and yeah.
But can we just listen? I think we will generate quite some ideas here, at least on the level of keywords, key phrases, but just not to leave it in the air. Can you maybe send a couple of links to, I mean, from your summer school that you found kind of particularly interesting, so that triggered some ideas in you to the mailing list, or to me directly? I will summarize them and I will distribute to the community.
Yeah, sure, no problem. I can send you an email.
Yeah, I think it's good. Okay, so shall we move on? So we do around the table and then so we see how it goes. Maybe so. Anybody?
I'll volunteer to go. I'll volunteer to go next.
Okay, go ahead.
Okay, so yeah, I wanted to mention three different things. Two of them are directly inspired by presentations I've heard here in this seminar, which is great. But so where I see potential for vector symbolic architectures is that I still think it's the best way of sort of understanding how we can represent more complex structures, complex structured information in neural type systems. And I'm totally amazed how far Chat GPT, how far transformers have got. The kind of results that you can see from Chat GPT are just amazing. I've been having conversations with it, and it can reason with theory of mind, which requires quite a bit of information. Because theory of mind is when you're reasoning. An example is like John was watching Mary put an apple in a box, and then John left the room, and Mary switched it to a different box. And when John returns to the room and wants the apple, which box is he likely to go to open to get the apple? And that requires, reasoning about what John knows and what he's seen and what he hasn't seen and what Mary knows and all of that stuff. And ChatGPT can solve those kind of problems. It denies having the ability because it's got these safety measures that in it that says it doesn't have a mind. So when I asked it, can you reason with theory of mind? It says, no, I can't because I don't have a mind, but here's what theory of mind is. And it explains theory of mind. And then I ask it a theory of mind problem and it a puzzle and it solves it correctly. And so, but where I'm going with this is that the it seems to me still that the way the information is represented in these huge transformer networks is opaque. We don't know what it is, and you can trick these things up, but I'm not sure if you can trick them up any more easily than you can than you can make an ordinary person stumble with these kinds of problems. But it is completely opaque to me and in how it's representing this information. And obviously it's doing some kind of binding. And so my thought there is that could we build something that's like a short-term memory for it that it can use to keep track of what it's reasoning with? Just, you know, like a better blackboard that it can use, using vector symbolic, you know, and make the operations that it can use on that, implement them with vector symbolic operations. So that's sort of one idea. The other really interesting direction, another was the talk from Frank Key on graph embeddings. I think that's a really interesting direction to go, and that was using tensor products with no attempt at compression, because that was what worked for that particular domain. So I think that's another really interesting direction to explore. And then the third was the talk from Mohammed Alam and Edward Raff on the HRR former, where they were taking the vector symbolic operations, the HRR operations, and using those in the attention layer. And the results that they were showing were phenomenally good. And the potential there is it could be just a much more efficient way of doing what attention networks need to do. And these large networks are incredibly expensive and slow to run. And so if you can speed them up considerably and maybe make it much cheaper to have wider vectors in the that they're working with, then that might open up other kinds of capabilities as well. So that's what I wanted to say. That's what I've been seeing as some interesting opportunities. But I'm very interested to hear what other people have to say as well.
Yeah, I'm just me myself. I'm looking through the notes. I mean, again, just to maybe quick reflections on what you said. So that's in my mind. So that what you said about structuring the information inside these large models or explainability. So that sounds. That sounds interesting. Absolutely. So that's.
I think was it some work from Abbas Rahimi's group? They had an interesting system which was sort of a hybrid of deep learning and HRR type approaches, which I think might speak partly to your interests, Tony. I mean, in their case, I think sort of the latter stages, which are more let's call them the reasoning stages, were sort of standardish VSA HTC types of approaches, but the initial stages were deep learning. So they were essentially transducing from input signals, sensory signals, to vectors, but where they wanted the vectors to have the VSA HTC types of properties, and so they put in a loss function and various other bits and pieces so that it was actually trying to learn vector representations which had the algebraic structure which could then be used by VSA HTC. Although I think what you were suggesting sounds sort of more like the opposite direction of feeding VSA-ish kinds of stuff in and allowing the Chat GPT or whatever to to sort of work directly with those rather than just arbitrary mush vectors that people normally use.
Yeah. Who? I didn't catch the name there, Ross.
I think it was from Abbas Rahimi's group at IBM Zurich.
Yeah. Okay. Yes.
I think it might not actually be out yet, but so I don't know. But certainly I've seen some work from them along those lines.
Okay, thanks.
No problems.
Yes.
Okay, do you want me to jump in quickly? Okay, I'm me. I've been around for 1,000 years. I'm living in Melbourne. I don't get paid to do this stuff. I work in credit risk modeling. That's my bio. Okay, programs currently working on the sorts of things I'm doing at the moment. I'm very slowly implementing my own package in R to do this kind of work. I don't expect anybody else to find it useful. I just would to support my own work. But the two things in it that might be of some interest are the random selection bundling, which Mike Hedis, I managed to nag him into implementing that in the Torch HD Python package, and also a generalized cleanup operation. Not particularly useful from an implementation point of view, but just from the point of view of experimentation, because it's generalized. It incorporates, it allows you to implement most different sorts of cleanup you could possibly want, including sparse distributed memory as special cases of this generalized structure. So that's that. Oh, the other thing I'm working on at the moment is finally trying to write up properly the error correcting VSA. So this was used, Simon Levy and I did use this in our work on distributed analogical mapping. But essentially it's sort of a module which incorporates binding and unbinding, but in such a way that if you have a noisy queue and you're retrieving from the memory, the retrieved value is closer to the correct retrieved value than the queue is to the noisy queue is to the uncorrupted queue. And that has some interesting relationships, I think, to other things like the relationship between Hadamard product BSAs and HRR and tensor products. So that's possibly interesting. Things I think would be interesting to see work done on. This is getting back to Tony's point about Frank. I missed his name in the talk. Is it Frank Chu or Frank Chi or
QUI? Which I think is pronounced Chi, but I'm not sure.
Okay, Bruno's nodding. I think we'll take that as a yes.
Frank Chi, yeah. That's right.
Thank you. Okay. Yeah. So I mean, so he was making the claim in there that the tensor product is, if you like, the canonical form of binding, and just from his slides, the diagram he had in there looked like it was a category theoretic proof. So I'll take that as being a yes, that's a reasonable, perfectly reasonable and valid claim. So I'd be interested to see, although I probably don't have the skill set to do it, some kind of a proper mathematical investigation of what algebraic properties of the tensor product are lost under different sorts of compressions down to a lower dimensional projection of that product. So you'd imagine that if you took a tensor product and just set one of the elements of the outer product to 0, that the overall impact on the algebraic properties of it would be relatively small. So it'd be interesting to see which things like commutativity and associativity and so on disappear or are replaced by approximate versions of themselves under different compressions, with the aim of that being to say, well, what are the algebraic properties that we rely on in doing this work, and therefore which ones do we not care if we lose them in the compression, which might then give us a means to to then design VSA HTC operations, which retain some of the products, which some of the algebraic properties, which are essential. I mean, one of the things I saw that Frank used in his talk was he had an example of edge composition in with the graph embeddings, and he was saying that in tensor products, if you compose the edge AB with the edge BC, you got the edge AC. So it was a tensor contraction. So basically the composition directly represented the composition of those edges, whereas in most VSA-ish HTC type of systems, you'd rather get something which looks more like a sequence, ABC out of it. And that's fine. But on the other hand, do we actually, if you were trying to represent a sequence rather than that exact composition, having that property of your binding operator would be a pain in the neck. So it'd be interesting to know which properties do you actually need to do useful things, and then if you like custom designing your operators to suit that. Well, we got the other one. What do I think would be interesting to know about? Oh, actually, no, the other thing I think would be really great to see work done on is just more in general with resonator networks, especially with a more symbolic version of resonator networks. I mean, the sorts of problems that people have been working on so far have been, if you like, decomposing perceptual structures which are based on continuous quantities like locations in the XY plane and so on. My interest would be more in, can we do the same, but where the objects are more like graphs or discrete structures in general, because then that, to my mind, is getting much more like cognitive problems like analogy and so on. So if I can take a graph and I can substitute different labels onto the vertices, then arguably you're doing something that looks like analogical mapping in that. Okay, that one quickly. Final thing, interesting area to know about adjacent areas. One of the areas that I've looked at, which I think is really interesting, and they appear to know nothing at all about us, is the quantum natural language processing crowd. So there's a group of people who've been around for 10, 15 years, and they've basically been using category theory applied to linguistic problems, mapping the solutions they come up with into into finite vector spaces. So it turns out there are various sorts of grammars which are useful for doing linguistic-y things with, and there are category theoretic models of that, and it turns out that the category theoretical model of these grammars can be mapped onto the category theoretic model of finite dimensional vector spaces, and that in turn relates to quantum mechanics. And so they have these wonderful looking diagrams where they're drawing, they have this formal diagrammatic calculus where basically you're drawing these diagrams which represent structures in these spaces, but they actually correspond to proofs about what's going on, and there are people then trying to map these onto real live quantum hardware at the moment. So I think they've got a really interesting mathematical basis for dealing with the kind of stuff that we deal with. It's just because they get the full tensor products for free out of thinking I'm going to implement this in real live quantum mechanical systems, they don't have to worry about the compression. So it'll be just interesting to see what their thoughts are on this. Let's try to compress this to get this onto non-quantum hardware approach. That's it, I'm out.
Yeah, thank you, Ross. Any reflections, immediate reflections, comments?
One of me. Oh, go ahead.
Oh, sorry, Tony. Shall I go?
Yeah.
Oh, okay. Mine was super quick. Just Ross, can you send some links to some of those papers?
Yeah, shall do. So specifically the quantum NLP ones?
Yeah. Yep.
Okay.
Yeah, I just wanted to say a quick comment related to that last point about quantum NLP. I think it was probably Pente and I from this group. Last week we were listening to a seminar by Martha Lewis I
Yes.
think she's one of these persons, and she honestly she gave quite a bit of credit to VSA in her
Oh, really?
talk.
Okay.
So she touched on it a couple of times at least. And that was at Santa Fe Institute. So she was giving a talk at Santa Fe Institute last year, and it should be recorded. So it might
Oh,
be
good.
released at some
Dennis,
point.
if you come across a link for the of the recording, can you send it over? Because
will have
I
to look
couldn't
for
find it directly on the seminar page.
I only noticed that it was recorded, but I don't know the details about the release of the recording. But it was definitely recorded, and yeah, I think it was of course high level talk, but they looks like they've even used the idea of role filler binding in some of their experiments. So it's yeah, pretty interesting.
Yeah.
So I guess Ross, you've kind of convinced them to look into role filler bindings. That's what I wanted to mention.
I think.
eventually.
Well, I think that. I mean, that's an ancient idea, and there's probably some maths around to say that it has to be that way. I didn't have any hand in that. I actually have spoken to a couple of the people involved some while back. So I mean, there are some of them who did. At least I bent their ears on the relationship, but the people who are working most directly in the hardware, rather than sort of more just sticking with the abstract approach, are perhaps the ones who appear to have the least intention to reference across to other areas. But I mean, there's no particular need for them to do that anyway.
All right. Dennis, do you want to add anything? I mean, since you were last taking the mic, you want to add anything from your side?
Yeah, sure. Am I allowed to share the screen? Yeah, I have a single slide for each.
Wow.
Okay,
cool.
Yeah. So basically, what I wanted, I mean, to talk about, and I think this is still interesting, and this is underexplored part, is like we had that recent paper, like several of us here co-authored this paper, where we talk about that idea of computing and superposition. Basically, the fact that we have this linear superpositions allows us to do something interesting, and like probably the minimalistic example of these interesting things is a Bloom filter. It's a minimalistic example that has proven itself to be very useful, and I mean, unfortunately, it was like developed outside of VSA, but it's a perfect example of, in my eyes, this is a perfect example of minimalistic VSA approach. And so, of course, we sort of tried to approach this or it was actually this year. So we were trying to sort of continue on this idea, and this is also relates to Ross's points on trying to use the resonator network. So the idea that somehow if one wants to do something interesting computationally, we would like to do some kind of dynamics to form VSA representations, and then being able to sort of run these dynamics by resonator network in order to get basically the answer to the question we were trying to ask the system. And in this case, we're doing the semi-prime factorization. It was like a neat example to do it, but it wasn't like very practical. And I personally was thinking for a while on the 3-SAT problems, more of a like standard classical problem formulation. But I haven't, have to admit that I dropped the ball a little bit. Like I get the system that was working on it, that was solving SATs problems, but it was very unclear like how good it was, how efficient it was actually. But I think this is something interesting to me. It still sounds like listening underexplored direction. So the question is there anything that VSA could bring on the table for solving these sort of constraint optimization problems, in particular trying to leverage the ideas of the resonator network, given their sort of theoretical efficiency on just factorizing this kind of compositional representations that like of VSA style. And then a little bit of a related thing, which I just saw last week, but there are like no perfect connections to it, is this paper called Continuous Black Box Optimization with an Eisen machine. And so basically in this paper, it was kind of surprising that they're using that they use a similarity preserving encoding. That was actually Dmitry Rachkovsky was actually one of the authors behind that kind of encoding. But it's basically an encoding that allows one to create similarity preserving binary vectors. And so here the authors were trying to use this idea, as I understood, to actually get binary formulations of continuous problems and then being able to sort of map them to Ising machines and probably they were trying to use like a quantum solvers for Ising machines. So that was kind of their interface. So this kind of binary similarity preserving encoding was a way to sort of, you know, fool the system and get into the binary representations, solve, you know, an Ising machine, get a solution, and get them back to the continuous values. Didn't fully get all the details, but that was sort of, I thought that was kind of an interesting idea. And it doesn't really connect perfectly to this computing and superposition, but perhaps there's something together. And two other unrelated things that I wanted to say was, one is like, this is something I'm trying to do these days. After listening to the webinar about Torch HD, I was trying to contribute, and my personal reflection is that it's a little bit hard to get into that development mode, but I think it might be a good resource for the community to have many of the primitives and ideas being implemented in the Torch HD. And I was personally mainly trying to help at the moment with first like making a sort of a benchmark for classifiers, because there are so many works on classifiers and they're often just tested on just a couple of data sets. This is a little bit dissatisfying to see it. And so one idea that just having, you know, like a playground with a large collection of data set that is easily accessible would simplify the benchmarking and just trying different ideas on such a collection of data sets. And another thing which Antonella asked me to promote a little bit, but since he's not able to join today, is that Antonella Rosata, who I think he was given a webinar at some point here, and he's with La Sapienza University of Rome. He's trying to organize to co-organize with this date conference a workshop on VSA, which is going to be like, I think, kind of mid-April. And so that's going to be an in-person event. And I guess at some point there will be email to the community list promoting the workshop and, you know, collecting the interest. So that's yet another opportunity to share the ideas, and yeah. So something similar to what we're trying to do today, but in person. Yeah, that's it from my side.
Thank you. Dennis, also, would you send this slide to me? So
Yeah, sure.
Now looking at your presentation style, so I think I will start. I have an idea of starting a shared document, like a Google presentation or something. So I will incorporate your slide and whatever ideas we're discussing here, so that everybody can come and edit. So I will send the link.
Do you want the raw, like PPTX or PDF?
PowerPoint, if possible.
The PowerPoint, oh, sure. Mm-hmm.
All right. So by the way, so since Dennis mentioned this Boolean functions, and I see, yeah, and I see Hedda is here. So what's new on your side, and what do you think is challenging and interesting to think about?
Yeah, so I've been working on a couple of things. On the one hand, incorporating some ethical reasoning into my system. I am a little bit on background, so I have a I wouldn't call it neurosymbolic. I don't very much like the approaches they use. I've been looking into that a couple of years ago, and it's more like hybrid AI. You plug together two things, and it's not well connected, the two parts, from my point of view. So my approach was rather VSA based, and having a coming from the direction of activation patterns and context activations. So context in a double role on the one hand, to provide a form of symbolic reasoning, and on the other hand, to so the contexts in my approach are like the basic symbolic building blocks. Everything is context. So this can be a sensor value or a moving object in space or whatever. And so those are the logical main ingredients, and they are also the symbols then, of course. And then to combine on the one hand, the learning and discovery capabilities of the VSA with logic reasoning that is possible by looking also at the same structures as logical bit vectors, but with a little bit different operations. So what the system can do is it is a full reasoner, but also it can recognize and memorize configurations. What I've been working on is, since the system is now able to I've given a presentation, so it can it gets a text as an input, and then it from this text, by the logical mechanism itself, it can construct a layout of whatever it has seen, or of whatever it has gotten as an input. This is possible because logic language has an inherent semantics. And this is kind of new, but this has also been recently, 2020, confirmed. There's been a distinguished paper award at ICHCAI confirming just that result. Unfortunately, I wasn't the author, but that's now that's been confirmed. I've been working on since my system is very memory hungry. I've been working, besides applications in ethics and also creativity. I've been working on reducing, on compressing the memory requirements. What Ross mentioned, that sounded all very interesting. As long as I don't have a quantum computer, compressions are what I'm looking at right now. But I'm also doing this in my free time. Professionally, I have to work on databases. Okay.
Thank you, Henra, for the update. I my little eye looks Bruno maybe. So he's the central
Hey,
frame. Yes. Hi, Bruno.
okay. Hi, everybody. So yeah, I'm Bruno Olshausen at UC Berkeley, and I work a lot in problems in vision, computational models of the visual system. And so we've been looking at the applications of HD computing or VSAs to visual scene analysis. So basically, the idea of describing a visual scene as a superposition of bindings of objects and where they are in the scene. So this is started with work that Eric Weiss started in the lab around maybe 2016 or so. And similar kinds of things have been done in Chris Eliasmith's group, I think, more recently. And so that seems to me a very promising idea of how to approach the visual scene analysis problem, of how you can form a compositional representation of an entire visual scene, which I think something that's kind of stumped the field for a long time. We still don't have good models of how the brain does that. And then in particular, more recently, what I find most exciting about this whole approach, and what seems to me extremely promising, and it'd be nice to see further development on, is this whole idea of computing in superposition. So what the resonator network is doing, taking a vector which represents a binding of several different things, and then factorizing that apart. So this problem of factorization is really central to perception. You see it just comes up over and over again in all the problems of perception and cognition, that you have to factorize some kind of a representation into its constituent parts. So for example, in vision, just taking a picture of a square and factorizing it into the invariant part, which is the shape, separate from the transformation that's been applied to it. And there was some work that David Airthorne did a number of years ago in the map seeking circuit, and that's always seemed very promising to me. But I think what this the resonator network and the VSA approach sort of gives a way of formalizing that a bit more, so that to me is a really sort of promising area of being able to search through the superpositions. This is kind of like the unique property of representing things with high dimensional vectors, as you could add them all together in the same space, and they survive that superposition. So now you can sift through many combinations in parallel. So I think that's, and then maybe in terms of your third question again, what would be in terms of adjacent areas. So one is I think the link to coupled oscillator models. So this is work that Fritz and his student Connor Bybee is doing, and they've been doing, and also Paxson. It seems to me there's very interesting connections there in terms of how coupled oscillator networks could solve these factorization problems potentially, and give a link to circuits in the brain that might do this. And then also to the work that Tony mentioned has been going on in transformers. There seems like a lot of connections there between the kinds of operations that transformers are doing and the binding operations in VSA and so forth. And if that could be formalized, it seems like it could be a interesting direction to explore.
Thank you, Bruno. I actually maybe I want to insert a bit of my ongoing work just in connection to what you said about factorization, the importance of factorization, and the idea of resonators. I just want to give you some visual idea very quickly. No slide, but something that visualize the ongoing work on my end. So if I just share my screen and show you here. So do you see this web page with the graph?
Yep.
Yeah. So the idea is, I started to look at the usage of VSA for implementing some basic learning basic learning functionalities like unsupervised learning. So we published recently a paper in TNNLS on which is called algorithm called Hyperseed. What I'm working on now is it's an extension where you could basically convert the problem of unsupervised learning to the problem of factorization of data that you have at hand. And so what we are working on now is a concept that I don't have a stable name for it. So it's either a network of resonators or graph, resonators graph, so to say. So this graph, for example, shows a set of identified resonators for this, favorite dentist problem of classification of 21 languages. So you have text written in 21 languages encoded, well, basically n-gram statistics using VSAs, but then you kind of try to find resonators, configuration of resonators that react on different parts of the data set. And here that what we kind of identified, so that so for example, this is totally kind of unsupervised, and the idea is that during this unsupervised learning process, you learn the configuration of resonators. So each block, each circle here is a resonator, and as you see, so these resonators are marked after hand. So basically, by observing the actual labels falling into these resonators, and so then you can also build a graph of how this resonators are connected with respect to similarity. So kind of the bold lines are kind of most similar, and the this thin lines they are less similar, for given samples. So this is a kind of ongoing work on my side, which I find kind of interesting. And the idea is that you can do this kind of resonator-based learning for virtually any data. But again, so the details probably is best to be explained in the text and paper. So let me stop sharing the screen. And on the open problem side, so since I'm talking here, so I think it would be interesting to revisit sparse representations and VSAs based on sparse representations. To me, I just stumbled on plenty of problems, working with them. So because they are not same flexible as, for example, dense representations. These block-based codes that are used now, they're very restrictive in terms of what you can do with them. Like if you want to use combinations of permutations, binding and bundling, so then it becomes very cumbersome to work with such representations. Moreover, and binary sparse representations, they are also very restrictive. What I have currently in my mind, it would be interesting to have a kind of hybrid architecture, which is work across sparse and dense representations, and also binary, hybrid in many senses, like binary, hybrid to complex representations, sparse, dense. So interplay between all existing approaches would be interesting to see. So that's kind of my 10 cents to the discussion.
So yeah, maybe let me jump in here, Yevgeny. Since we are actually, so I'm Fritz Sommer. I'm also at the Redwood Center at UC Berkeley. I'm also working with Mike Davis on neuromorphic implementations of VSAs. And so naturally, we are very interested in the efficiency of more the implementation side of VSA. So what's, you know, what kind of coding of hypervectors should we use, and how does this actually then manifest in resource use? You know, and there's, of course, there's different resources, you know, it's just the hyperdimension, but then there's also for the cleanup, the memory that you need. There is, you know, for binding and bundling, there is resources that you need to spend in order to do such an operation, computational, also in terms of circuits and wiring. And so we are looking also into sparse implementations that are these block codes, but we are also actually working on kind of new kind of block codes that are actually somewhat less, that sacrifice a little bit of the sparsity within the blocks, and then actually gain other interesting properties like you know, interpolation properties if you want to encode analog variables like locations of objects and things like that. So yeah, so that I also find very interesting. And but maybe just to give you some other ideas. I mean, there's lot of stuff was already brought up. I will not repeat these interesting directions. But I'm also thinking really in terms of connections to neuroscience, which I'm interested of, because I think neuroscience right now also has a problem in interpreting these very, very high dimensional recordings that they can do now from actually working brains that perform certain tasks. And also in terms of modeling. So I think actually VSAs can also bring very interesting kind of, you know, transparency properties into modeling, and also maybe into some approaches to do data analysis. And what I'm very intrigued about is still that we, you know, in VSAs, we often have this very holistic approach that, you know, the hypervector just, that everything you store in the hyper, or you represent in the hypervector, is distributed across all elements. And that's, of course, not like what we see in the brain, right? So there is some modularity, but then you have mixed selectivity. So there is a lot of also holistic properties that things are actually mixed together, even in a single neural activity of a single neuron. So I find this very interesting. And of course, block codes are somehow something in between. So I'm very interested in this question. And then another restriction that I see in a lot of VSA algorithms is also that we try to squeeze everything in one hypervector, right? So if we learn from a data set, we try to form a hypervector by superposition also, and that then contains information of many data points. This can only be done so far, right? At some point, you cannot, if the data set is very, very large, you cannot just make your hyperdimension commensurably large. So you need actually also to think about how to come up with algorithms, with VSA algorithms that do not squeeze everything in a single, all the knowledge from the data points in a single data vector. So you need entire architectures that also use, you know, memory of synapses, not only to do the cleanup, but also to actually just hold all this information that you actually can learn from a large data set. I think this is also something which is missing in a lot of the VSA literature, because we often look into these toy problems. So anyway, I will stop here.
Thank you, Fritz. Listen, once again, I think it would be a good idea to, I mean, now thinking more about it, of having this document that summarizes all the ideas being discussed, and maybe so I even think structuring it based on names of presenters. I have some bullet points annotated after your presentation, so maybe you can complement it later on the web, so if you find it suitable.
Sure.
Yeah.
So
Thanks. So first of all, I see some new people joining. So, and those probably are again missing the actual time of start of the webinar, but cool to see you guys. Pentti.
So I had a quick question.
Yeah.
Quick question for
Yes.
Bruno
Yes.
or
Tony, please.
Yeah, a great question for Bruno or maybe Fritz. Very interesting what you were saying about superposition. This at Google, what I'm seeing is people are using transformer networks and embeddings everywhere, and it's been very successful. But the embeddings that are being used are they're vectors, but they're relatively low dimensional, sort of 32 element or 64 element, and that is not enough to support superposition and retaining information. And so Bruno, I was interested in your comments, and I was wondering is there any evidence that with seeing how successful people are in using these relatively low dimensional embeddings and not using superposition at all, I was just wondering, am I barking up the wrong tree and thinking that superposition might be useful? And so Bruno, question for you or Fritz is do you see any evidence in the brain that superposition happens and is utilized as a useful construct?
I mean, there's definitely this concept of mixed sensitivity in neurons. So for a long time, people always thought, there's maybe one feature which is represented in a spike rate. And now people looking into neurons in prefrontal cortex and so in really higher, more cognitive brain areas, they find very often this, what they call mixed selectivity, which could be a hallmark of actually superposition of many things represented even in the activity of a single neuron. So I think there are some, and people don't really have a good understanding of this yet. It's very rudimentary how this is also investigated, because it's often much of the data is still very low dimensional. And then often if they come to high dimensional data, then they just ask the question, is there maybe a low dimensional manifold which is just somehow pushed up into these high dimensions, but what really counts is just then where the point is in the low dimensional manifold. So I think people somehow ask the wrong questions. They don't really ask in neuroscience still the right questions. And this is where I think VSA as a theory could also help the neuroscientists to actually maybe ask different questions with these wonderful new recording techniques that they now have. But Bruno, what do you think?
Yeah, I echo exactly that. I mean, that's what's so exciting to me about this. And this is exactly what theoretical neuroscience is trying to do. We're trying to think about ways the brain might be doing it, right? That we haven't thought about yet. And this is one. I mean, it's just like when you start to think about this whole idea of superposition, it almost feels to me like the brain has to be doing something like this. How could it not be? And so no, I mean, but to answer your question, Tony, I can't think of any explicit evidence where someone has shown, oh, here's some evidence for superposition in the brain. But that's just because no one's looked for it, and no one's looked for it because we've not even talking about it that way up to now. It's a relatively new way idea. It wasn't until my student Eric Weiss developed this idea of like visual scene analysis and superposition. I mean, it hit me like a brick. I hadn't thought of anything like that before. It was just like, it was totally wild. And yeah, I mean, I think it's very exciting that like what Fritz said, we're getting all these parallel recordings now, and people are finding word vectors in the brain. They're getting a lot of mileage out of regressing word vectors to fMRI data and things like that. Well, maybe we could then think about bindings, right? A word vector is a binding of, it's like it's part of speech and the semantic content. And so I've been talking to some people at Eddie Chang's lab about maybe trying to do that and looking for, that might be a more meaningful way of disentangling, what's going on in these ECOG arrays and things like that. So no evidence right now, but I think there's tons of mileage there to start looking for things like that.
Okay, there's very weird things. So for example, people who study the visual system, right, they all of a sudden find that there's actually a lot of hallmarks of actually motor signals in the visual area. So all these, the specialization that we say, oh, primary visual cortex is just concerned with the visual input, seems wrong. So there's a weird stuff at points in that direction.
Oh, great. Now, first of all, so I think we consumed 1 hour, so that's great. I guess since we are still here, so it is an indication that we can continue for some time more. So, but if you have other appointments, so of course you can watch the recording afterwards. So, but I don't want to stop at this moment. So I'd rather pass the mic to Pentti.
Okay, can you hear me?
Yes.
I prepared some points on just how this area compares with something that's already sort of well established. And I see that the AI and the machine learning world really have a poor understanding of what computing with vectors is. And well, it's just linear algebra, so what else is new? I think that's sort of reaction. But I think there's also curiosity out there. And so we should look at what we as an area of field can do to help people understand what computing with high dimensional vectors is. And so here's sort of several things. First of all, I think would be very useful to have well-documented examples that are easily understood of things where the vector symbolic architectures sort of differ from traditional methods. And this is like combining symbolic and data-based learning or continuous learning, which is lightweight. In other words, it's actually can be carried out in relatively small computing structures. And then sensor motor integration. I think sensor motor integration will be one of the things that over time will be seen as well. This was a very hard problem, and it seems to be that computing with vectors provides a very natural solution. So in general, I'd say let's see what happens in the animal world, but at various levels of intelligence, and how those things as a model for what we can do in biology. And another point that would be very helpful, and that is having exercises for students. Because when you try to do something that has already been done with a different way, you really learn not only what has been done, but when you face the problems and try to solve the problems, that usually is a way to come up with solutions. If you just take a very superficial point of view of the area, then well, it'll still be a year from now. What else is new? I mean, it says linear algebra. No, it is not just linear algebra. And then the third thing that would be very good to have is have meaningful standards of comparison. By meaningful standards, I mean something that goes far beyond percentage correct. And because that percentage correct does not take into account the amount of work that went into getting that percentage correct. So this notion of state of the art, when the state of the art to be as percentage correct, it really hides all the work that it goes into getting something correct. Like training time and execution time, complexity, flexibility, and scaling. You know, how does your algorithm fare in terms of such criteria? And I could talk a little bit about the work in progress I think what I'll do here is I just leave it at here on those points that I think would help our area to sort of make progress. And I think the important thing is really to get funding. So I will send these notes to our collection, including the work in progress. But those were the points I wanted to bring out. I mean, just how to move this area forward, and some ideas. And I'm sure you have further ideas, but mainly get people to be exercising this thing and just working and finding out, because eventually the people who build hardware, they need to know what matters and what doesn't matter. And that's the only way we can find out what matters and doesn't matter, is just doing these exercises. So that's my spiel of the day.
Okay, thank you, Pentti. I want to transition to somebody that I am curious to hear from, because I saw some names appearing during the webinars as listeners, but I never had an opportunity to talk to a person. So I see Marcus. So can you probably take over, introduce yourself, and tell what you work on?
Hey, thank you. Yeah, I'm Marcus. I'm working at Brandenburg Technology University in Cottbus in Germany. So the group I'm working in mainly uses ideas from quantum mechanics, so mainly the tensor product representation. And we're working on what we call quantum-inspired cognitive agents. So it's a technical system which tries to solve different problems. And it's an overall system with a perception action cycle, quantum logic inspired classification, and quantum inspired ontology inference. So that's mainly my part, this ontology inference. And we're trying to compute out of the received data from the sensory machinery some sort of theory about the causal dependencies in the environment. So it's some sort of functional dependencies or something. And we're only at the beginning. So, but the fun part comes in if we're using superposition to represent the structure, what the agent thinks the world looks like. So, and what I'm trying to do next, some other interest is some sort of integration of tensor product representation and Petri nets, because in Petri nets there's a thing called concurrency, so it's independent parts of computation, so that seems a natural thing for superposition. But when you think about it, there is some double meaning of superposition. So on the one hand, it's this sort of concurrency, so independent things, and on the other hand, it's like in what's it called, the bundling. So it's not independent, but it's everything in the same set. So that's for me kind of interesting thing, this double meaning of superposition. Yeah, thanks.
All right, thank you, Marcus. I personally, I would be happy to invite you to one of the webinars. So if you have an idea of a talk you can give, so please drop me a line.
Okay, yeah. Thank you very much.
So it would be interesting to know more. I mean, even if it's not kind of directly related on BSS or something, so this reflections on quantum mechanics, quantum cognitive agents. So that's that sounds totally relevant and interesting to hear. Let me jump to Graham. So we have a couple of more people to go.
Okay, yeah. So yeah, I was really interested in Fritz's comments because I presented in the past some of the work that we've been doing with spiking neural networks using a slot encoding. One of the interesting things that I think I mentioned, and Fritz picked up on it at the time, was that rather than when we're doing the bundling operation, rather than using an argmax to trying to select the position of the spike in our slot, we just choose the position of the first spike. And that remarkably seems to work well all the time. We managed to get the sort of bundling capacity that we predict, and it's just as good as taking the argmax. And I don't know whether Fritz has had a chance to think about why that is. I think it's just a statistical thing. You've just got enough slots that it doesn't really matter whether you choose the first bit position or you choose the argmax. But one of the benefits of that for the work that we're doing, if you remember, the work we're involved in is service discovery and workflow orchestration in edge of network environments. And so the idea of using superposition and passing a single vector around that represents the whole workflow is a very nice mechanism. And the properties of the hypervector, the sort of holographic representation within the hypervectors is also beneficial, because all we need to do, if we know how many vectors we're bundling together, we can just truncate the vector and transmit truncated vectors if we've just got a few vectors that we're bundling together. So you can dynamically change the vector size very easily, pass it around the network, and services can describe themselves, and you're basically looking for the best matching vector as you unbind or unbundle the vector. But trying to do that with spiking neural networks is the thing that we're really interested in. Can we do it in an ultra efficient way? And the slot encoding seems to have benefits if you want to do time to spike encoding. And the other thing about the slot encoding that we found was that you can do incremental binding. So you don't need to do a normalization step. You just keep bundling the vectors together, choose the time of the earliest spike in each slot, and that mechanism works perfectly well. And the advantage of that for us is that as we're constructing our workflow, we actually can then build incrementally a vector that describes the current state of where we are. And we can sort of share that vector around the network to say, well, we've got so far through the workflow. So using sparse encoding is really interesting to us. And if there are other sparse encoding techniques, that's something we'd be really interested in looking at, and then trying to map those onto neuromorphic architectures. The challenge we had with the scheme that I presented was that we needed to represent time delays at the synaptic connections, and that's quite a costly thing to do. But of course, if you think about it, you can do the same thing with a weight and a leaky integrate and fire model. So I'm currently working on trying to build cleanup memory using a leaky integrate and fire model. That means I don't need to store time delays. You can just think of the synaptic connections as a weight and a leaky integrate and fire neuron. So that's the sort of thing I'm playing around with at the moment. Oh, and I'm also interested in transformers. I tried to build the attention mechanism that was described. We've had a couple of papers presented at the webinar on attention mechanisms, and whilst it's true that the attention mechanism is sort of an analog of an SDM, a sparse distributed memory model, I'm not convinced it is a true attention mechanism. I've just tried to implement it using an SDM, and I couldn't get it to work anything like an attention mechanism. So I may just be misunderstood the presentation, but if anybody's got any ideas, or if anybody's tried to replicate the presentation we had using an SDM, I'd be interested in having a chat offline. So that's where I am. I think the challenge for us is to try to get more people in the United Kingdom interested in VSA. We've got a number of customers for the sort of things. I'm at Cardiff University, or I work as a contractor for Cardiff. We've got a number of people coming to us very interested in VSA and what it can do for them. But they're saying, well, where are the other centres of expertise? And of course, they're not in the UK. So if you'd all like to come and live in the UK, that would help me.
All right, that sounds locking and attractive. Okay, thank you.
If you do know of people working in VSA or HDC in the UK, if you come across them, just do let me know, because it's quite important for us to be able to.
I think we have one person, Graham, or even a couple of persons on the HD Computing website listed.
Have we? Yeah.
And yeah, I'll come back to that.
Thanks, Dennis.
Person.
Yes. Listen, we have a few more people to hear from. Before passing the mic to the next speaker, I want to quickly share my screen and show that the web page for the webinars was updated, or I updated it just before the today's session. So as I said, so most of the slots until April are filled in with speakers. So, and we will start on January 23. I will not go through the available confirmed talks, so have a look yourself. But I see that we have one of the one of the future speakers here with us. So Madison from University of Groningen. So maybe that would be a transition to your part. Hi.
Ah, lovely. Yes. Yeah. So I'm a Brit. So sorry, Mr. Graham, but moved over to the Netherlands. Yes, I'm in the bio-inspired circuits and systems group in the Netherlands. So a neuromorphic group. So at the end of the day, I guess we'd always like to build some chips, but then so using normally analog spiking neurons. But then, of course, I've lent towards VSAs as kind of a model that we should be looking at first before we immediately jump towards building a chip, before we understand kind of, we have something interesting that we could implement. So, for example, with VSA techniques. So recently, what I've been looking at, and indeed what I'll be presenting in April, is how we can use kind of conventional attractor networks, how we can use VSA techniques to give attractor networks like Hopfield models, for example, more functionality. So obviously, we quite like building attractor networks on chips because they're very stable and robust. So if we can utilize VSA techniques to give them more functionality, so in particular, how to let them represent, this is what I'll be presenting, how to let them represent any arbitrary state machine just by using binding operations and kind of masking operations of certain neurons, which we could easily achieve on chip. Yes, that's what I'll be looking at, what I'll be presenting. So basically, VSA techniques apply to attractor networks. With regards to what I'm doing kind of immediately, so what I'd like to do in the future, I guess, is then extending this to continuous attractor networks. So if we take, for example, fractional encoding techniques, can we then let attractor networks do, can we then have continuous attractor networks do more interesting things? I don't know. That's what I'd like to start looking into. But then I guess more long-term is, I guess, in the same vein as everyone who's already mentioned kind of, well, I've spoken about resonator networks and what we can do, what we'd like to do with them, for example. So if we could do similar things in terms of letting attractor networks utilize some sort of vector symbolic representations which let them do some sort of more complex reasoning by using VSA techniques to let attractor networks do some more complicated tasks. I guess would be something I'd like to look into. But then with regards to something that then I should be looking into in order to I guess achieve this goal, is the fact that I presume a lot of other more learned people have already had a thought about what kind of the atoms of logic should be and reasoning. So if I could then look into a field like that, which I guess might be neurosymbolic computing, I'm not sure, see if we can transplant that over to VSAs and then also plonk that onto attractor networks to be able to enable them to do more interesting tasks, more interesting reasoning tasks. So that's my overall direction I'd like to go in is more interesting reasoning using attractor networks, exploiting VSA techniques. And then in a completely different direction, because someone mentioned sensory motor processing using vector symbolic architectures. So since we're also a bio-inspired circuits group, one thing that we very much like to do is build chips to do spatiotemporal processing. So something else I'd really like to look into and see more coming out of, I guess, we'll see more vector symbolic trickery applied, would be the question of how to do, I guess, clever spatiotemporal processing using VSAs. So for example, there's the stuff that Paxton Frady was doing with the similarity preserving encoding projecting onto a layer of resonator neurons in order to do spatiotemporal processing, but only in a feed-forward manner. If we could find similar tricks to be able to do cleverer signal processing using spiking networks, and that would also be very good and something I'd like to look at. That was slightly too long, but that was 20 cents of information.
Okay, thank you. All right, Tony, I have to jump for yeah. All right, thank you, Tony. Thank you for being with us, and Happy New Year to you. Then so we have a couple of more people.
I think.
Yeah, sure.
Head is asking to get in.
Yeah, sorry.
If you're looking into what kind of basic objects you could have in a logical language, that was one of the key points where I started off. The idea was to have just one type of entity. So I call it contexts, but it can be any sort of thing. And that corresponding to a vector, so an activation pattern. And I built the whole logic structure on top of it. So at the topmost level, you have real first order logic, so quantifier and all. So that's quite convenient, but it is built one layer upon the other. That is a difference to some of the other approaches where you always have to say, okay, how do the predicates and the arguments come together, and that's all. There is a correspondence there between VSA operations and how you can build that up. So
yeah, for sure, that sounds exactly what I need to look into in terms of I guess how to having some sort of logical structure which I can map over. So yeah, thank you very much.
Yeah.
So now I'm looking at black square with Nathan on it. So Nathan, are you still there?
Yes, I'm still there, but I got to drop off in just a minute. So right quick, thank you all very much. So I'm work at the United States Air Force Research Labs. I'm a basic researcher in applied mathematics. And our group is particularly interested in sequential learning, being able to detect anomalies and then accommodate them into our machine learning system. In particular, our particular interests are looking at by analogy, you have a biological organism, it's got a myriad of diverse sensors, but at the end of the day, all those sensors have to be converted to a spike stream of some sort to be processed in the brain. So can we modularize machine learning? Instead of training artificial neural networks as a monolithic entity, training an artificial neural network to generate sparse feature vectors, then mapping those feature vectors into high dimensional vectors, the hypervectors to do hierarchical machine learning on subsequently. So that's a lot of where we're looking at, and especially putting that on a size, weight, and power limited system. So think satellites, think radios, things of that nature. Areas of interest to throw out there. I'll throw out 3 papers. One was a paper that was already presented. That was the IBM Zurich, where they were doing their constrained fuse shot class incremental learning. They were using, I think it was ResNet 12 as a feature extractor, and then mapping that to those hypervectors. Trivially, it allowed them to add categories, to add new instances of information. So that's a particular interest. Another paper just came out was Wolfgang Moss and Chris Stockel, I think. It's cognitive map learners. So that's not hyperdimensional computing, but the idea was that you're training an entity. It's supposed to be a robot or something like that. It makes an observation of the world. It needs to learn a representation of its state, and then its goal is to learn, given a finite set of actions, if it takes a particular action, what state is it expecting to be in the next instant? And in that way, if they changed the goal of the robot, whether it's to run away from a predator or to attack the prey, it doesn't have to relearn motion. You've just changed, a higher level entity would decide which state it needs to be in next, but you don't have to relearn the neural network connections to do all this. For that particular paper, they had like 3 different neural networks to go and it rhymes with some of the work that Marcus described here, and some of the pocket research I've been looking at is, can we make these states hyperdimensional computing vectors and then do subsequent computing on that, do some interesting stuff on that. So that's stuff I'm playing with. And then the last paper I'll mention is work coming out of Tom Cleland in Cornell University, and I forget the paper name offhand, but they're doing research on external plexiform layer networks of the mammalian olfactory bulb, how mammals smell. And there was some really interesting work on applying sheaf theory and some category theory for incipient category generation. And then I'll pull further, and I think a couple people have mentioned this as well. For that, so it was a modular neural network, so it was very easy to add new knowledge without retraining the entire neural network. But you would work with a high dimensional pattern representation, but it didn't have to be random, the way we typically generate random hypervectors. And I know a couple of people have mentioned, if you're not enforcing random hypervectors, how does that affect the mathematics? What can we do with that? And they were interested in using completely random hypervectors for, like I said, incipient category representation. You throw something out in the wild, it's not going to observe all possible sights or sounds or smells it could ever possibly observe. So how do you effectively partition the finite neural resources you have to account for the various odors or the various categories that you have observed, and then to be able to add in a non-destructive way those new categories. And again, they were mentioning using sheaf theory and other tools of category theory to do this. Thank you.
Yes, thank you, Nathan. If you can send me the links that you mentioned again, so that I can incorporate in my notes, that would be very
Certainly.
useful. Last but not least, I see Chris.
Hi,
And Stefan is joining, so we are getting more and more people. Okay, so but Chris, you are okay. You are not last and not least.
okay, yeah, let someone else, yeah, give the final words or remarks. It's fine with me. So sorry to join late, but I am very happy that the discussion has gone on for this long, and it's been really great to hear everyone's ideas and thoughts. I just wanted to maybe mention one anecdote that kind of is leading into some things I've been thinking about or interested in, which are, I guess, when to use completely random hypervectors in VSA and when it might make sense to actually use like the high dimensional geometry to create representations, whether that's with things like classification or things like word embeddings with like random indexing models. So part of the reason, or something I think that was exciting that happened was I'm a teaching assistant for a course on like neural computation that Bruno's teaching right now. And for one part of like a homework assignment, we actually had them implement a part of like a random indexing algorithm. And this is actually an assignment that we were able to reuse from the course we taught on hyperdimensional computing. I'm at UC Berkeley at the Redwood Center for Theoretical Neuroscience. And so we got to teach a course on HD computing and VSA last year, which was exciting. But yeah, Dennis and I worked on getting that assignment together, and Dennis did a great job of getting a nice kind of toy data set and making the assignment really accessible. But then as a result, some students who, to my knowledge, had not done anything with VSA before were so excited with that project that they wanted to compare like random indexing methods with Word2Vec. And I think it was cool to do that comparison because usually, as far as, yeah, I'm aware, like most people, like when they're asking about like random indexing, they usually tend to mention like, oh, how does this compare to like Word2Vec models, even though the random indexing models far predate. I think what got me thinking about was is to my understanding with like Word2Vec models, the continual embeddings that you're learning for different words is continually updating over time. Whereas with random indexing and starting with index vectors, those are random, but they're fixed. And then they're bound and permuted and summed together in order to generate your word vectors or your context vectors for given kinds of cases. And one area which I'm interested in playing this further is, so this generates a measure of similarity based off of this like distributional hypothesis to different words appear in different kinds of contexts. But there's no reason why words or like natural language has to be the only kind of application for this kind of algorithm. So I've been thinking about ideas of like, for example, sparse coding embeddings and learning those, and just more general, like the general problem being learning, and then also applying it to tasks other than like language. So I'm just throwing out a whole bunch of ideas here, but I just think it's a very kind of exciting intersection of a lot of different topics.
All right. Thank you for your input. Stefan, so you joined last, so I give the floor to you. So what's your insights?
Hello, Evgeny. Sorry, I joined very lately. I simply missed the time. And of course, I was very curious what you guys are discussing about. And so I was late. I'm very sorry. And
the recording will be available, so you didn't lose much.
This is good news. Yeah. You see, right now, I'm more interested in simply listening into which direction this community goes. Right now, I've listened to lots of applications, and these are certainly fine. On the other hand, as you know, I'm more a theory guy, and so would like to bring together really neuroscience and VSA, and I'm not so sure how they really fit together. And So this is one part. Now I'm working at INI here in Zurich, and so it's quite usual for theory to be quite close to experiments. This is one thing I would like to try to do, and the other thing is still it is thinking about operations on these very high dimensional binary vector spaces. And as I did in the a couple of months or even years ago, I don't know, I think that in particular the addition, the bundling operation should be there's lots of room to think about what this bundling operation is. I suggested a bundling operation which is not associative, which automatically makes it possible to store sequences without any positional markers or something like that. This operation I've now understood is quite close to what is called stochastic rounding, which is also used in this neuroscience field. And so I'm very much interested in giving this idea of very high dimensional, even high dimensional binary vectors, more theoretical grounding, so that it might be used also for dynamics, because having dynamics in this field, I honestly do not see. But you see, I'm more in the position of a listener, and trying to combine it. So this is so actual very concrete projects, no, but I still find this high dimensional computing is a very interesting computational method, because it really makes many things very much simpler. And so therefore, I think, but still, whether we have already right bundling and binding operations on hand, this is not clear to me at the moment.
All right. Thank you, Stefan, for your input. As I told previously, so I will summarize all the ideas which we have discussed today in a presentation. So I will share a link with all of you. So feel free to complement and comment on that document.
Yes, I will. Thank you.
Yes, but I mean, I think we are done with this exercise, and I'm very happy that it took well, almost 2 hours, of very lively discussion. So that's very great. So that went well beyond my kind of expectations. And I'm very happy to see you all here. So any last minute comments or wishes for the new year of VSA research, to be more precise? Well, if not, so let me officially close this session. So I think we shall repeat it once again. So let's aim for having such a discussion, either physical or online or hybrid, by the end of the next spring 2023 session of Vsaonline. So so let's hope for the productive season, and Happy New Year and Merry Christmas to all of you.
Thank you.
Bye, everybody.
Thanks again.
Yeah, thank you. Bye-bye.
Bye-bye. Thank you very much.
Thank you, guys. Bye-bye.